Okay, so if you are doing a resubmit on Human Response Times lab, first I would recommend looking under modules. You can also find it under assignments, but it's much easier, I think, to find it under modules because it's under the labs modules. Also, please, please, please review the style guide because people are missing tons of points because we spent half of a lab day going over the style guide and I think everyone's forgotten it. So please reread that, especially with regard to the size of the graphics. Okay, so if you go in here, you should find the link to the video link with, you should also read this, by the way. This is what I'm using to grade your paper. It's there. I made it public so you can see it, so you can know what to include in your lab. So if you go to this video link, you'll end up at this part, to this video. And what I would think should be the most rewatched section is around 4:30 to the end. It's showing you if you end up with just, it looks like stars in the sky rather than snakes. You want to make your graphics, the last 4 graphics at the end of the lab should look like snakes, not like stars. So I'm trying to, there we go. They should look like snakes, not like stars. So it should look like a snake with a red line going through it. So this is the part of the video you need to rewatch if this is your issue. However, I'm going to do something else with the rest of this video and I'll show you exactly what it's addressing. Okay, so people are not reading the double check before submission bullet points. So there are 4 scatter plots which are actually snakes at the end of your lab. The last 3 are specific to you. The first one is going to be very similar for everyone. It'll still be noisy, but it's this bit here, the 2 normal sorted distribution, normal simulations sorted. It should be right on the line of best fit, is it? And this is the part people are missing. Why or why not? People are saying it fits the line. A lot of people are skipping the why or why not. This is what this video is to address. Okay, so let me make some simulations first. I may as well show you how to sort this because you have to do this, and some people are still having trouble with this. When you're sorting, sort by itself, create a new column. Then you can hit options and do the next one, sort each one by itself and create a new column. So I have, in this mini example I'm giving to you, I created 2 different normal distributions. So I can give you a dot plot of all these and show you what they look like. So this exponential looks like this. These 2 normal distributions don't look the same. This looks completely different from this one, but you'll find out when I do, hopefully you'll find out when I do the QQ plots that these guys actually have the same shape. And you can see, like for example, if I do a histogram on these guys, you can get a general idea that they're the same shape. So this guy looks kind of bell-shapy, this one looks kind of bell-shapy, and this one does not. Okay, and so by looking at the same set of data through different lens, you have stronger statements or weaker statements that you can make. And so right now, if I graph a scatter plot of the sorted normal versus the other sorted normal, and I go ahead and put a line through it, I should see that they line up pretty well. And that's because similarly on the histograms looked similar. This bell-shapy curve, it looks kind of noisy, but the other bell-shapy curve looks kind of like this, and it's kind of noisy. But what this is doing, what this QQ plot is doing, this is a QQ plot. I didn't ask for a QQ plot. I asked to do this manually. I could also have done a QQ plot. I could say do a QQ plot of just one of them, because then what it's going to do, StatCrunch is just going to compare this against a standard normal distribution, and that's a little bit more esoteric. It takes a little more explanation to explain to you what's going on, and that is why we're not using the official QQ plot tool on StatCrunch, because it requires more explanation than what we are doing. We're just manually doing the same, conceptually the same thing. We are lining up all our data, and as for the explanation for why, but why does this work? how come when I'm lining up two things that have the same shape, why will they line up roughly on a line? Okay, so let me just show you what happens when you don't do it that way. Why does it not? It doesn't look like it's on a line. It trails off here and here like a smiley face. It doesn't touch the line down here or over here, right? What is going on? So what is happening? Because these two lines have, these two sets of points have essentially some kind of relationship, I could compare one against the other. One way you can think of this is SAT scores versus GRE scores. If they both map back to a typical standard normal curve, then the relationship between the two looks kind of like this. So what this is saying is my original mean was 0 and standard deviation was 1 for the first one, and the mean was 100 and the standard deviation was, I think, 15 for the second one. So what it's going to do is that's going to be borne out in the line of best fit. It's going to say there is a shifting component and there is a stretching component, and that is all that is allowed. Okay, so basically least squares regression or linear regression reflects a shifting and stretching component, slope and intercept respectively. If those are the only two actions that are happening on the data, you can kind of convert one set of data to the other. You're not going to get the same exact data back, but you're going to get something of the same shape. So for example, if we go back to this graphic and we said, oh, okay, so this one, the mean was 0 and the standard deviation was 1, I can say data compute expression that is normal 1 times the mean, which was 100, and then plus 15 or 25 or whatever it was. Let me figure out what that was. Okay, so I can go back and look at this picture and get a sense for what it was. It was plus 15 roughly. Okay, so I'm going to say converting normal 1 to normal 2. Okay, so in other words, I converted this data. Think about if you're converting GRE scores to SAT scores, or any two standardized tests, you want to compare them, but they have different mean and standard deviation. You're converting those scores, right? And then if I graph a, like a dot plot of, let's see, where's the dot plot? It would be great if they alphabetize these. So this guy versus, okay, what was my original control click? There we go, to get those two side by side. That was not what hold on, let me fix that. Well, I'm going to leave that in the video because I want to show you that I made a mistake, and that's okay, because I meant to say normal times 15 because that's the standard deviation and that is the new center. Convert N1 to N2, and then I should be able to graph some dot plots of normal 2 versus the converted data, and they should line up. There you go. See, now they line up. They didn't line up because I did it wrong. When you do the shifting correctly, and I took this guy whose center had been in 0, and I just added 100 to everybody, so the center is where it belongs, and I also multiply by 15 before I did that, so the stretch is right. Notice how these two sets of data are different, but they're both basically normally distributed. If I go like this, you can see it a little better. They're normally distributed with noise, and the noise is in a different place, but the centers are now lined up and the stretches are the same. And that's exactly what happens when you create this scatter plot and you put a line through it. It's just another way of lining these guys up so they're kind of back to back. It's like if you took a whole bunch of kids in 5th grade and a whole bunch of kids in 12th grade, and you lined each class, like 2 classrooms full of 30 students, and you lined them up back to back. But you line the shortest kid to the tallest kid in each class, and then you see if there's kind of a linear relationship between the two sets of kids. So if you look at the shortest kid in the 5th grade class and you say, well, I'll multiply that kid's height by whatever and then add whatever. So maybe we find out what the best fit line is and see if we line these kids up, if there is a linear relationship between the two sets. So if there is, then that means the only difference, the basic difference between the two sets can be accounted for by the model, which is simply shifting and stretching, which, after all, is a line. So if a line can do this, then that is demonstrating that the shapes were the same. Okay? And that's a little long, but you can simplify that discussion and you can encapsulate it in a paragraph that makes me understand, you understand that why this works. Okay, so I want some understanding that you thought about this and you understand why it works. If you have any trouble, please reach out to me or reach out to the TA for an explanation. We can Zoom with you. We can talk to you about this until it makes sense to you.